Okay, so the big theorem called the Fundamental Theorem of Calculus. Sometimes it's known as the first fundamental theorem of calculus because we're going to see also another one. But this by far is the most important, the most famous one, and it's going to make our life easy. It's going to help us find those areas under the curves in a much more efficient manner. Now, it's going to take us a few steps to get to the theorem, so please bear with me. I'm going to first start by reviewing what we know so far. So let's say that we have a function f of x over the interval from a to b. And let's assume our function is positive, meaning that it's above the x-axis. So we've already looked at how we find the exact area under that curve. We first try to fit in n rectangles under that curve, right? So if the curve is given by that red function, the red curve, first we try to put n rectangles under it. What was the base of each rectangle? We call it delta x, right, which is the length of the interval b minus a over n. And then we write down the partition points. For the partition points, you start with the left end point a, and then you keep adding multiples of delta x to get, from one to the next partition point. And to find the area, you basically sum the areas of n rectangles. And in each case, this was the base, right? And this was the height of the rectangles, because we plug the point into the function to get the height. So this is what we know so far. And we actually know one more thing. What was the exact area under this curve? We need to take a limit, right? To find the exact area, you take a limit as n goes to infinity of the above. So what you see right here is going to be the exact area. So this is the definition of the area under a curve. Limit as n goes to infinity, summation I goes from 1 to n, f of x sub I times delta x, a very complicated looking expression. So I guess mathematicians realize this is a very cumbersome notation, and they try to simplify it by choosing another notation. So to replace the first two things, to replace the limits and the sum, which is a lot of cumbersome notation as you see there, they decided to use an elongated S notation, which is something like this. So I guess from the Latin word like sum or summa or something like that. So they decide, okay, when you have an infinite sum, we're going to represent it by an elongated S. Okay? So from now on then, for area under a curve for a positive function, we're just going to use this notation. So exact area equals, and it's equal by this new notation that we're seeing. Instead of the limit of a sum, we're using the elongated S. And notice that on that S, you can also put the left end point of your interval and the right end point of your interval. So this represents, we're going to find the area from A to B. And you see in there, in our definition up there, we had f of x sub I times delta x. In this new notation, you see how that shows up itself? F of x sub I shows up as f of x. Again, they're trying to simplify the notation even further. And delta x, how did that show up? As just dx. You see, it's really the same thing in a sense. So f of x represents the height of each interval, dx represents the width of each interval, and the elongated s represents the summation of those areas in the limiting case as n goes to infinity. So all of a sudden, we have a much simpler looking notation. Okay. But it still didn't tell us, how do you evaluate this? All we know is, okay, it's simpler notation, but how do you calculate this in a simpler way? That has not been answered yet, which we're going to try to do in the next slide. But let me just tell you this much. This works for positive functions, right? The graph has to be above the x-axis. But if it is below the x-axis, there's a very easy fix. You take the absolute value of the result, basically, because there the heights are negative. If you want area, you convert the negatives into positives. You can still find area with similar methods. OK, now let's take a look at the statement of the fundamental theorem. OK, so let's suppose that we have a function here. This red curve is y equals to v of t, the velocity function. So an object is moving, and we know its velocity at any given time t, where t is in hours. I think I'm going to fix this just a little bit. Make that 50 up there. OK. OK, the first thing I'm going to ask you guys from this graph Again, my goal right now is instead of just stating what the fundamental theorem of calculus is, which is very easy to do, I'm going to try to give you some idea behind, how could Newton and Leibniz have come up with this great, fantastic theorem? What could they be thinking? So we're going to try to derive it ourselves in the next 5 minutes or so. So in that end, we're looking at a specific function, not just y equals f of x, but the velocity function. And for the velocity function, I want us to think about what does the area under the curve represent for the velocity function? Because think about it, Newton was also a physicist, so it's quite possible he was dealing with the velocity function. He looked at the velocities of objects, falling apple, planets. So what would the area under this curve represent? Well, I did 2 rectangles there. You could put, of course, more rectangles. First, let's go 1 rectangle at a time. What is the area of the first rectangle? The base is how many units? The base is 1. And the height is, assume it's like right at 60. So the height is 60. So that's the area of the first rectangle. What is the area of the second rectangle? The base is 1 and the height is 50. And think about what the units are here, okay? On the base is time. So you have like 1 hour. On the y-axis, you have miles per hour, the velocity at which this object is going. It's accelerating, it's decelerating, it's going faster. But between 1 and 2 hours, it went at 60 miles per hour, right? So if I multiply those 2 quantities, what will I get? I get the total distance traveled in 1 hour, correct? And what is that total distance traveled in 1 hour? It was 60 miles. This object traveled 60 miles, although this is just an approximation because this object was not traveling at 60 miles an hour the entire 1 hour, right? Because if you look at the graph, it keeps changing, right? It keeps changing. Like first it was maybe at 40 something, then it was a little bit faster, then it was a little bit faster. But we assume in that time interval from 0 to 1 hour, it's going to travel at a constant of 60 miles per hour. Obviously, this is not going to give us the exact answer, but the thinner your rectangles, the more accurate you're going to be in estimating the entire area, right? So again, finding the exact area under this curve will give us the exact distance traveled by that object over that time interval. So what are we getting then? We're getting 110, right? So what does this 110 represent once again? Total distance traveled from where to where? From the first hour to the third hour. So total distance traveled. And one way to represent that would be like this. Remember our s of t function, which represents distance traveled, the total distance traveled up to a point t. So I can represent it like this. S of 3, this is miles traveled in 2 hours, from the first hour to the third hour. I can represent it like this. S of 3 minus S of 1. Again, if S of t represents the total distance traveled within t hours, so if I know, let's say this object is going, from here to Jacksonville, and you're trying to say, okay, how much did this object travel between the first and the third hours? So if you know where this object was, how many total miles it traveled by the end of the third hour, maybe this object traveled, let's say, 200 miles by the end of the third hour, right? And if you also know where this object was by the end of the first hour, let's say that was, it was 90 miles was traveled at the end of the first hour. So how much was traveled between the third hour, between the first and the third hour? So you say 200 miles minus 90 miles, that would be like 110 miles, right? So in other words, S of 3 minus S of 1 gives us the total distance traveled between the first hour and the third hour. Now, another way to write S of 3 minus S of 1 okay, I want to see. Okay, I think I'm going to get back to that in a little bit. But right now, let's then try to do the following. Let's get to the next line. The integral from 1 to 3 of v of t dt. Remember now, what does this represent? The area under the v of t curve from 1 to 3. And based on what we just found, what is that area equal to? correct. And remember, we just learned this notation. Let's review the notation. The notation, if you have like f of x dx, that gives you the area under f of x from a to b, right? In this case, you have integral of v of t dt. That should be the area under the v of t curve, the velocity curve from 1 to 3. And what do we get for that? We just got that, right? What was the area under that from 1 to 3 hours? 110 miles. And one way to write that, we agreed, is the displacement, s of 3 minus s of 1. Distance traveled up to the 3rd hour minus distance traveled up to the 1st hour. That difference is the total distance traveled between the 1st and the 3rd hours, right? Okay. Now, I'm going to write this in one other notation for you. Would you agree that velocity is the first derivative of distance? We've seen it a long time ago, right? S prime of t is the same thing as velocity, because S prime is the rate of change of distance, right? That's velocity. Okay, so instead of v of t in this next line, look what I'm putting down. Instead of velocity, I'm putting down S prime. Can I do that? In other words, is velocity the same exact thing as S prime? It is, right? Remember, this was like when we did the applications of derivatives. The rate of change of distance was velocity, remember? ds dt or s prime was velocity. So this is a legitimate substitution then. I can replace velocity by the derivative of the distance function. They're the same things, right? Velocity is the same as s prime. Everybody agrees with that? Okay. So let me write the answer once again. So if you're integrating s prime of t, the answer turns out to be s of 3 minus s of 1, based on the graph that we've just seen. Now let's try to do the next one. The next one, I say forget about the distance function right now. Mathematicians, they don't like to put themselves in a small box saying we're only going to deal with the distance. They want to generalize things like y equals f of x. It could be any type of function, whether it's representing blood flow or whether it's representing flow of traffic from an intersection point. It's the rate of change of something you have, f prime of x right there. Based on the example above, what do you think the answer will be for any function f of x? We don't have just distance function right now. If you were integrating s prime of t, answer was s of 3 minus s of 1. If you're integrating f prime of x in general, what do you think the answer will be? Following the same exact pattern. Would everybody agree? F of 3 minus f of 1. Would everybody agree? What's the pattern that we observed here? If you have the derivative of the function here on the left-hand side, on the right-hand side, you have the function's antiderivative, basically, right? So if it's f prime, you're going to observe just an f over here. Now, mathematicians, they like to make things even more general. Instead of f prime, what if you had, just f of x, what I have on the bottom here? If you have just an f of x. And if you've seen this before, please don't give me your answer. I want to have the other students who have never seen calculus to think about this answer. So if on the left-hand side, what I have is f of x, what do you think I'm going to have on the right-hand side? And you can say in words, because there you may not have an equation for it. You can say in words. What would you want to see on the right-hand side? So when you saw f prime up there, f of x showed up on the right-hand side, right? So if you have f of x on the left-hand side, what function do you think will show up on the right-hand side? What is the relationship from f prime to f? The antiderivative, right? So when you have f of x on the left-hand side, you're looking for what then? You're looking for the antiderivative of what? Of f of x. And we usually represent it by capital letter F. So the antiderivative of f of x, which is capital F of x, will show on the right-hand side. And first, you're going to plug in, again, 3 minus, you're going to plug in the lower limit, 1. Again, where capital F represents the antiderivative of lowercase f of x. So, but the general idea is this. If you were integrating, or I shouldn't use that word, if you were finding area under velocity, or s prime, here you end up with s, right? So if you're trying to find area under f of x, you should end up with the antiderivative of the f of x function. And voila, we have our famous fundamental theorem of calculus, which we've just did it together, we derived it together. I should say it's not a real rigorous derivation we did, but we just tried to understand where this formula comes from, this famous theorem. So it says basically that if you're trying to find the area from a to b of a function f of x dx, all you have to do is find the antiderivative of the function and evaluate it only at 2 points. This is like magic. You don't have to know the function in between a and b. You just have to know it at the 2 endpoints. So you plug the upper limit first into your antiderivative minus the lower limit. This will give you the area under that curve. Now, it looks very suspicious, right? It looks too easy to be true. Let's check a few things that we've already done, see how it works, things that we already know the answers to. For example, we've already done x squared in this class, right? And what was the answer? We did it in our last class. The area under x squared should be what? 1/3. I also have it on the board for you over there, right? Now, let's do it with the shortcut method, see how easy it will be. OK, to find the area under x squared, we need to first find the antiderivative of x squared. What is the antiderivative of x squared? X to the third over 3. And the notation we use is we put a line here saying that we're going to evaluate this from 0 to 1. And based on the fundamental theorem we have just seen, which number are you going to plug in first? Let's go back to the theorem, look at it. You always plug in the upper number first. You see, f of b goes first. So plug in the upper limit first into this antiderivative function. You'll get 1 over 3 minus, so this is your f of b, minus, go ahead and plug in the lower limit now, 0. 0 over 3 is 0, of course. So what do we get? 1/3. Amazing. You could have done it in your head. It could take you probably like 1 second to do it, right? As compared to like, maybe 15 minutes to develop that idea last time, even maybe half an hour. So things are much easier with the fundamental theorem. And I guess that's why it is called the fundamental theorem, because it takes something so difficult or tedious and changes it into something so simple and easy to evaluate. Now, we've already done x cubed in your group activity, right? And we went over it earlier today on the board. So what was the answer to this one? When we did it a long way, the answer was, look over there, it's on the board. The answer was 1/4, right? Now let's do it with the fundamental theorem. Again, that took us a long time to do, right? It was tedious. OK, find the antiderivative of x cubed, x to the 4 over 4, and substitute the limits. Always plug in the upper limit first. That's your f of b. So you're going to get 1 to the 4 over 4 is 1/4. Then substitute the lower limits. And that gives us 0. So the answer is 1/4. Once again, a very tedious problem turned into something very, very simple. But it is important, I think, to know what's going on behind, this. It's also known as the integration symbol, the elongated s. What's going on in this process? Again, there's a lot of theory behind a simple shortcut rule. And the theory relies on what we saw last class, which is basically Riemann sums, the infinite summation limit as n goes to infinity. OK, before we do this example I have on the board, I want to do that other one we did at the beginning of this class and last class, the integral of x squared. Let me do that one. X squared, and the limits were from 1 to 3. And the answer we had gotten earlier, that was a lot of work. We got 26/3, remember? OK, let's check this one right now with the fundamental theorem. OK, first thing we're going to do is take the antiderivative of the function x squared, which is exactly x to the 3rd over 3. And then we're going to plug in the limits we're going to go from 1 to 3. And we start with the upper limit always, because the theorem says f of b minus f of a. So this number is a, this number is your b. So first let's do f of b. So plug in 3 in there for x. You get 3 to the 3rd over 3, right? Minus, plug in the lower limit now for x. You get 1/3. Simplify. Did we get the same answer? We sure did in like 5 seconds. Right. So the method, the fundamental theorem really makes our life easier. However, this too will get messier because, of course, the math books, we take an idea, we beat it to death. We give you all sorts of examples you can possibly see on it. So you will see very complicated functions now, not just an x squared, but maybe 5x cubed minus root x plus 17x squared, something like that. So this too can get a little bit messy, but still, it makes the other process much, much easier. Let's do the one I also have here written in black ink. Integral from 2 to 5 of x squared plus 2. Let's do that one as well. Okay, I'll give you a minute to do this one. So we first take the antiderivative, right? And the antiderivative of 2x, 2 is 2x. Then we plug in the limits. Always we plug in the upper limit first, right? Minus the lower limit. And the way I'm going to combine them, I'm going to first combine the whole numbers. Right, that was a plus 4. So to combine the whole numbers, I have 10 minus 4, that's 6. And then I'm going to combine the fractions together. And it's 8/3. That's like 1/17 plus 18/3. It's like 1/35, I believe. And I think this one actually turns out to be a whole number. I think it goes into, is it 45 times? Yeah, 45 times. So the answer is the area under this curve from 2 to 5 is going to be equal to 45. Okay. Any questions so far about the fundamental theorem? Any questions? Okay. Yes? This is the limit. If you were to do it the long way, first you would do like a sub n using like n rectangles. You use summations to simplify. Then you take a limit. At the end of all of that, you would get 45. So in a sense, you have now a powerful tool to check your answer. So you can go back to the last section. Many questions you were maybe struggling with it there. At least now you know what the right answer is because you can integrate it, get the right answer. Now, if I say find the area using 20 rectangles, it's not going to be exactly 45, but it shouldn't be like 75. So it should be something in the vicinity of 45. Maybe you get 40 or 47 or something. Because if you had 20 rectangles instead of using infinitely many rectangles, but still, you should be in the ballpark of the exact answer. So this is a great tool also to check the answers from the last section. Yes?